Hello everyone, this is Jared back with another example. This time we're doing a combustion problem. This one is 13.18 in the 6th edition. We're working with butane as the working fuel and 150% theoretical air. Our goals for the question are to balance the chemical equations for normal and theoretical air and find the dew point temperature. And with that, let's move right into it. So first, we have to write out the equation for our fuel and air mixture reaction. C4H10, C4H10, which is our butane, and it is reacting with some amount of air, we don't know yet, which is this quantity, representing the air, our O2 and N2. And it is forming some amount. I'm going to go ahead and just write these. It's BH2O. There is some water coming out. We don't know how much though yet. Plus C, I think it would be, yeah, plus C N2. We don't know how much nitrogen's coming out. And some number of CO2, carbon dioxide. And so we need to find what each of these mean, and now this is A. See, and we need to find how much is coming out from our initial reaction. So let's start off by doing the carbons. There's a couple. There's a couple ways to actually do this part. You can just find out the total number, or you can solve it sort of like a system of equations. They're the same way, but just however one makes more sense to you. So obviously on this side of the reaction, we have 4 carbons total. As you can see, there's no carbons in the air, and there's only 4 here. So we have 4 in the fuel, and this has to be equal to the amount on the other side. And on the other side, there are no carbons here. There are no carbons here, but there are carbons here. We have D number of carbons, right? Because D times this C has to be the number of carbons over here. So it is just equal to a singular D. So obviously we have 4 is equal to D. And then on the next one, do the H's. And we have 10 H's here, no H's in the air, which means this side has 10 H's. And that means we have to have it equal to the other side. And now, as you can see here, there are no H's in nitrogen, no H's in CO2, but there are H's here. There are exactly 2 of them. So that must mean that on the right side, the product side, we have 2 times B for our number of H's. And that is simply because there are 2 already over here. We're doing this monotomically, which means we are accounting for every single one of them, not just H2 as a compound. And so we know that if we write the rest of this out, move over the 2, we get B is equal to 5. And now we have to balance the oxygens. So we have O. And notice I'm not writing O2, I'm writing O, because we are once again doing this monotomically. And so over here we have 2 O2s, an A, and there are no other O's anywhere else. So we have 2A is equal to, there are O's in this one, it's BO's, right? BO. So we have just B plus, no O's in this, but there are O's here, 2 O's, which means 2D. And now, if we solve this using the values we got earlier, we will find that A is equal to, so if you put 5 in here, you have 5, put 2 in here, you got, so 13 divided by 2, was that 6.5 or something? Yeah, is equal to 6.5. And this is just substitution, moving the D in here, moving the B in here, and you can solve for the A. And then the last part is to do the nitrogens. And now this one, I'm going to do diatomically because it just makes sense to do it like that, because if you do it like that, look at the left side of the reaction. We have A times 3.76, 0.76. That's how many on the left side. We have A times this right here is equal to C. Because there's no ends here or there, you just have it here. And the reason I did it diatomically is so I didn't have to like divide by 2, basically, because you'd have to multiply this over here to get a full number of just ends, and then over here is n2, so you'd have to it's just easier, I think, to do it this way. But like I said, as long as the products equal the reactants, it doesn't really matter how you do it. And when you do this value, you get C to be equal to, let me see, I think it's 24.44. Let me make sure of that before we move on. Yep, 24.44. So this right here so basically we have the balanced chemical equation. You just have to put them in here. So I will do that really fast. So it's C4H10 plus 6.5O2 plus 3.76 into, and this is going over, and we have B, which is 5H2O plus 24.4 into plus 4CO2. So this is the first part of part A. You have balanced it for normal air. Just 100, like, so we just found the normal air amount over here, and now we have to do the second part, which is balancing it for 150% theoretical air. So let's move on. So once again, I'm going to write this at the top. H10 plus, and then this part though stays the same. We know our coefficient for air on the normal reaction, and we know that we're doing 150% theoretical air, so we must multiply by 1.5 here. And then we write our normal reaction. Mind my bad handwriting. And then, let me see how I did that. Oh, B, so it's B. I want to make sure I'm using the same numbering system, or lettering system, plus C in 2 plus D CO2 plus, now this time though, since the last reaction assumed that all the oxygen was used up and we don't have any excess, but this time around there is excess because we're putting in more oxygen, more air, which means we're putting in more oxygen and nitrogen to the reaction. So let's do the same thing again. So C, we still have 4 C's over here, and there are no C's anywhere else. So very obviously we have 4 is equal to D, like we did before. And then the H's, still 10 H's over here, and on the other side there are still 2 BH's. So 10 still has to be equal to 2B, which equals 5. And then over here, let's move on to the oxygens. O's. That means, so over here now, we have 6.5 times 1.5, which is 9.75. So 9.75 times 2, because remember we have 2 O's here. And there's no O's anywhere else, so that's all we have on the left side, is equal to B, and that's from the H2O, plus 2D, which is the same as it was last time, only this time around we have an extra thing, which is 2E, which is the excess number of O's on the right side. And so if we solve this, which you can at the moment, because you have this number, you have B and D, which means you can get E to be equal to 3.25. Alright, and then, moving on, we have the number of nitrogens, so the N2s. And this is the same thing that applies. We have 9.75, right, over here, which is our coefficient for the amount of air. And this is times the coefficient of our nitrogen, which is 3.76. Let me get that number. That's 36.66. And then on the other side, we obviously have no n's here, no n's here, no n's here. So we have C, which is equal to 36.66. Which means our balanced equation is then C4 H10 plus, I think, what was that, 9.75? Yeah. Times O2 plus 3.76 into, goes over, and we have B, which stayed the same, which is 5H2O plus C, which is 4, or wait a minute, oh, that's right, I didn't, as nitrogen first, which means we have 36.66 into plus D being 4 CO2 plus E, the number of oxygen left over, as 3.25 O2. So this right here is the second part of part A. So we have now balanced the equation for both theoretical and normal amount of air. And now part B asks for the dew point temperature. And so the dew point temperature is basically the amount, or it's the time in which it's the temperature in which like liquid will start forming through, I think, just cooling. And so basically we have to, this is going to be working in terms of water. So we have our reaction done previously, which is right here. And so we have to work in terms of the water, when it will start forming like liquid water. And so we need to find first our partial pressure of our products. So first part, our partial pressure. Partial pressure just means that all of the components together make up the total pressure, which in this problem is 1 atmosphere. We're just assuming that. And so those all together make up 1 atmosphere, but we have to find what water only makes up. So to do that, we have to find the mole fraction first of water. So the mole fraction, I think they represent it as Y. So the mole fraction of water is equal to total moles, or it's N of water. So the number of moles of water over N of the products. So, one sec, let me make that a little better. And this notation for N and N products, that might be different in the book. I'm just using N's there. And so our number of moles of H2O, if you refer back to the previous slide, we have 5 of them, right? Because that's on the product side, which means we need to put our 5 moles over here. That's going to be annoying. Alright, so 5 moles of H2O. And now the other ones together, I'm going to go ahead and just calculate it, because I think that's pretty trivial. Everyone can just add the total number of moles, which is 5 plus 36.6 plus 4 plus 3.25, which is 48.91. And that right there gets you the partial pressure of water, or the mole fraction of water, I should say. 10. And then from there, we move on to the partial pressure. So the partial pressure of, partial pressure is equal to the pressure that we have, so I guess our P1 value, which in this problem is 1 atmosphere. We're just working under that assumption. And it's times the mole fraction of what we're working with, which is H2O. So we have a partial pressure of 1, or well, it would be 1 bar, I guess, 1 atmosphere, but they're the same thing. They're, well, very close to the same thing. How about that? And so then times our 0.10222, which gets us 10222. And so the next part of this is, now that we have a partial pressure of water, we then go to the liquid water, the water table. This table is table, let me find the actual table number for everyone. It is table, like, I think A2 maybe? Yeah, table A2. This is the temperature table. This is the one you want to work with. So table A2. And so what you're going to do in this table is you're going to go down the temperatures and find a pressure that is very close. This is a saturation pressure. And you're going to find one that is very close to your number. You can interpolate between it, 2 temperatures, to find exactly where your, or it'll be 3 pressures. You can interpolate between 3 pressures to find where your temperature is, and that temperature is your dew point temperature. So for instance, for ours, you would be interpolating between T1 to be 45 BC, T2 to be 50, and then it'd be P1 is 0.09593, P2 to be 0.1235, and then obviously we use our P number right here. And if you do this, part B, the dew point temperature is equal to 46.5 degrees C. And that's done through interpolation, or you can just guess a value, but interpolation works the best. And so with that, that is the end of the problem. I hope you guys learned something, and see you next time.